Welcome to The Explainer. Today, we're taking a seriously incredible journey right to the bottom of the Earth. You know, when most of us picture Antarctica, we tend to think of it as this completely static, white, frozen wasteland, just miles of ice, right? But the reality is actually far more dynamic than that. Today, we're going to essentially use that ice as a time machine. We'll explore Antarctica's shockingly lush prehistoric past, uncover a massive, watery underworld hidden beneath the ice today, and project a highly consequential and completely divergent future for the entire continent.
Okay, let's dive right into this, because to truly understand where Antarctica is heading, we kind of have to completely shatter our current mental model of it. What if I told you that the South Pole wasn't always covered in miles of solid ice? What if instead of a frozen desert, it was literally teeming with life?
Picture this, roughly 90 million years ago, during the mid-Cretaceous period, there was actually zero land ice cap at the South Pole. None. Instead, it was a lush, swampy, temperate rainforest. We're talking average annual temperatures of around 12 degrees Celsius and really balmy summer temperatures hitting 19 degrees. But what makes this absolutely mind-bending is that this vibrant ecosystem survived and actually thrived despite being plunged into total darkness during a 4-month polar night. Imagine that, a third of the entire year with absolutely no life-giving sunlight, yet the region was covered in dense vegetation. It's not exactly your typical beach vacation climate, but it is an absolute biological marvel.
Now you might be wondering, how on Earth could we possibly know all of this? Well, the answer actually lies buried deep beneath the sea floor. Scientists drilled sediment cores near the present-day Pine Island and Thwaites glaciers, and when they pulled up a section of dirt that had originally been deposited on land millions of years ago, they noticed a really strange color. By running it through CT scans, they uncovered this densely packed, fossilized network of roots. The preservation was so incredibly pristine that individual cellular structures were literally still visible, along with pollen spores and the very first remnants of flowering plants ever found at these extreme latitudes.
But this ancient forest presented a massive puzzle for climate modelers. To maintain those warm, ice-free temperatures that close to the South Pole, greenhouse gas levels had to be radically different than what we previously thought. Before this amazing discovery, the general assumption was that global carbon dioxide concentrations during the Cretaceous were right around 1,000 parts per million. But this new evidence proves that CO2 levels actually had to be much higher, between 1120 and 1680 parts per million, just to sustain that rainforest. It's a really powerful reminder of how intimately tied the Antarctic climate is to the atmosphere.
All right, let's fast forward from the deep past to the hidden present.
The subglacial underworld.
Right now, beneath the modern ice sheet, which averages over a mile thick, by the way, lies this vast, completely invisible aquatic underworld. And the sheer scale of it is staggering. We're talking about subglacial lakes. These are bodies of liquid water trapped right between the ice sheet and the solid bedrock down below. Now, you might think the extreme cold would just freeze everything solid, right? But geothermal heat radiating up from the Earth, combined with the immense pressure of the ice pushing down from above, actually keeps this water perfectly liquid. Over 600 of these lakes have already been discovered, and predictive models strongly suggest thousands more are just waiting in the dark.
To map out this complex subglacial network buried beneath miles of solid ice, scientists have to get pretty creative and look for clues on the surface. We use airborne ice-penetrating radar, which sends signals down through the ice that bounce back a little differently when they hit liquid water instead of hard rock. We also use satellite altimetry. That measures the incredibly subtle rise and fall of the ice surface as those deep lakes fill up and drain out. It turns out there is an entire hydrological network of lakes, rivers, and creeks down there completely cut off from the sun.
But here's the catch. Not all of these lakes behave the same way. We essentially have two main categories: active lakes and stable lakes. Stable lakes are usually found deep in the central region of Antarctica. They're quite large, and they pretty much just stay put. Active lakes, on the other hand, are highly dynamic. They're generally smaller, located much nearer to the coasts, and they rapidly transfer enormous volumes of water over really long distances. This triggers massive subglacial floods that literally lift up and lubricate the ice sheet above them.
When you actually map this out, the relationship is undeniable. The stable lakes just sit quietly in the slow-moving interior of the continent. But the active lakes cluster right near the coastal edges, perfectly aligning with the areas where surface ice velocity is the highest. These active lakes are basically greasing the wheels, accelerating the flow of heavy glaciers from the land directly into the ocean.
So, how do we learn more? Let's move to drilling into the unknown.
Understanding these lakes isn't just an exercise in ice physics. It's about biology and history, too. Because these waters have been sealed off from the atmosphere for millions of years, they could hold entirely unique microbial life and absolutely critical paleorecords. But to study them, we literally have to pierce miles of ice. It's a massive international engineering effort, and it comes with some incredible triumphs, and honestly some heartbreaking failures. Take Lake Vostok, the largest subglacial lake in the world, buried under more than 4 kilometers of ice. It was successfully drilled, but tragically, the pristine samples suffered from drilling fluid contamination. Then we have Lake Whillans, which was a massive success, drilled and sampled with 0 contamination. But these extreme environments definitely fight back. The attempt to drill into Lake Ellsworth, which is buried 3.4 kilometers deep, ultimately failed due to severe technical issues. The ambition is still going strong today, though, with massive upcoming projects targeting Lake Seas and Lake Snow Eagle.
The absolute biggest enemy in this field of science, though, it's contamination. If you're hunting for isolated, ancient microbial life, accidentally introducing modern surface bacteria or toxic antifreeze ruins the entire experiment. That is exactly why modern exploration has shifted so strongly toward hot water drilling. By using sterilized, heated water to melt a clean hole right through the ice, we can ensure these pristine, alien-like aquatic habitats remain completely untouched by human pollutants.
Okay, let's move to the final piece of the puzzle, the precarious future and the threat of melt.
We need to rise up from the bedrock to the surface of the present-day ice to really understand Antarctica's highly precarious future. Let's talk about ice shelves. These are the massive, floating extensions of the continent's land-based ice sheets. They serve a vital physical purpose. Think of them like massive doorstops that physically hold back the flow of the land-based glaciers behind them. If these ice shelves collapse, that land ice speeds up, dumps straight into the ocean, and that is what raises global sea levels dramatically.
The stability of those giant doorstops is almost entirely dependent on surface melt. Let's look at the timeline. Right now, in the present day, we're already seeing warming and localized ice shelf collapses. This happens when meltwater pools on the surface, wedges into cracks, and literally fractures the ice apart. Moving ahead to 2050, climate models show something pretty alarming, a complete doubling of Antarctic-wide surface melting. And here's the kicker. That doubling by 2050 is essentially locked in. It happens regardless of which emissions scenario we follow today. But as we look further out to the year 2100, the timeline drastically splits.
This is exactly where human choice steps onto the stage. Climate scientists use models based on different human behaviors. The RCP 4.5 model represents a reduced emissions scenario. Under this intermediate path, after that locked-in doubling of melt by 2050, things actually largely stabilize. There's relatively little increase in melting toward 2100. But then there's RCP 8.5. That represents a high-emissions, high-fossil fuel trajectory. Under this scenario, melting by 2100 doesn't stabilize at all. It accelerates wildly, completely surpassing the physical limits of ice shelf survival.
When you chart this out, the difference is staggering. Under the reduced emission scenario, you see the melt volume rise initially and then largely flatten out. But under that high emissions path, the volume of surface meltwater generated across Antarctica by the end of the century spikes so aggressively that it nearly rivals the immense amount of surface meltwater we're seeing in present-day Greenland.
To really understand what those melt volumes do to the ice, let's look at a specific threshold: 275 millimeters of water equivalent per year. This number right here represents the recent extreme melting rates currently observed on the Larsen C and Wilkins ice shelves, literally the highest melting shelves that exist today. Models show that by 2050, regardless of what we do, nearly 60% of the total ice shelf area on the Antarctic Peninsula is going to hit this extreme high melt threshold.
But then we have this number, 725 millimeters. This isn't just a fast melt rate. This is a historical, lethal limit. This was the exact intensity of surface melt that triggered the absolutely catastrophic, rapid collapses of the Larsen A and Larsen B ice shelves back in 1995 and 2002. Under the high-emission scenario, portions of nearly all the ice shelves on the Antarctic Peninsula will surpass this collapse-associated threshold by 2100. But under the reduced emission scenario, this widespread, lethal melting is overwhelmingly avoided. From a temperate rainforest born of naturally high CO2 to a hidden subglacial network of active lakes, Antarctica has clearly never been just a static block of ice. It's a highly sensitive, wildly dynamic system. But unlike the deep past, the next massive shift isn't being driven by slow, natural planetary cycles. It's being driven by us. The physics are incredibly clear, the thresholds are mapped, and the models are drawn. The door stops holding back the ice are melting. Really, the only unknown variable left is our behavior.
Antarctica's past is written in the ice, for sure, but its future depends entirely on our emissions. So which trajectory will we choose? Thanks so much for joining me on this explainer, and I'll see you next time.